Hi, my name is Emily Diana, and I am here today to talk to you about our paper, Lexicographically Fair Learning, Algorithms and Generalization. And this is joint work with Wesley Gill, Ira Globus-Harris, Michael Kearns, Aaron Roth, and Saeed Sharifi-Malvajerdi. And this is done at UPenn. So often we want our algorithms to treat different groups of people equitably. And one way to do this would be to apply a definition of fairness referred to as equality of group errors. So we would like to design an algorithm that makes the same number of mistakes on all groups. So for example here, if we have a hypothesis H1, the average error on group 1 is 0.5, average error on group 2 is 0.1, and average error on group 3 is 0.1. This would not be considered fair. H2 achieves average group error of 0.1 in all three groups, and we would call that a hypothesis that achieves equality of group error rates. Now, often there is a downside to this notion of fairness, because in order to force the number of mistakes or the portion of mistakes on all groups to remain consistent, we would often have to artificially inflate the error rates on better performing groups. So if the best we can do on group 1 is to achieve an error rate of 0.4, under the equality of group errors notion, we would have to do the same thing for group 2 and group 3, even if they're pretty easy to predict. So you can imagine that we might not actually want that. We might want a situation in which we minimize the error of the worst off group, and we still let the other groups have lower error. So for example, here we can imagine we have some hypothesis H1 that achieves the following group error rates: 0.5, 0.15, and 0.1. If we wanted to produce another hypothesis that was more fair in the minimax group sense, we might look at H2, which is going to minimize the error of the worst off group. So group 1 is the worst off. We bring that from 0.5 to 0.2. And then once that error is set, we can still do well on groups 2 and 3, achieving lower error. So although hypothesis 2 here would not achieve an equality of error rates fairness notion, it achieves a minimax group fairness notion and does at least as well on every single group. Now, you might ask, why stop there? Why minimize the worst off group and then just let all the other groups kind of do whatever they want? So you could think of this, you could imagine a recursive notion of minimax fairness, and this is what our paper is looking at. We call this lexicographic fairness, or lexi fairness for short. And the idea is that the number of errors made on the worst off group should be minimized, and then conditioned on that, we minimize the second worst off group's errors, and then conditioned on that, the third group. So we just recursively apply a minimax fairness definition. So again, here we have our hypothesis H1. We minimize the largest group's error. And then with that set, we look at the next two groups, group 2 and 3. We see that we can bring the error for group 2 down to 0.12 while keeping the error for group 1 the same, 0.2. And then after we've done that, then the only thing left to do is minimize the error on group 3. So this hypothesis 4 would give us a lexi-fair solution. Now, one thing to note is that algorithmically we can only ensure approximate minimax fair solutions or approximate lexi-fair solutions, because there's always going to be approximation error. So when we actually do our algorithms, we're going to have some kind of fudge factor, alpha or epsilon, that we allow. Now, this comes into play in this narrative because you can imagine that if we wanted to have an approximate notion of lexicographic fairness, we would want something that is pointwise close to the true Lexi-fair solution. So we might imagine that if, in theory, we could achieve this hypothesis H with group error rates 0.2, 0.15, and 0.1, and we want an alpha approximation, that we may get an approximate model H prime that just does alpha words on all groups. So now there's actually a problem with this notion of approximation, and that is because there's inherent instability in this notion. So you can imagine that we have a number of models, and for a specific problem, the true Lexi-fair solution is a model H1, which achieves the errors 0.5, 0.5, and 0. So we might imagine that an approximation would be H prime, achieving these errors 0.5 plus alpha, 0.5 plus alpha, and alpha. Now, when we actually go through the process of finding the solution, you would imagine that we find the minimax error rate for the first group. So let's say that our model class H consists of a number of different models, and we can find randomized models in this class. So we're able to find some randomized model that achieves an error rate of 0.5 plus alpha, which is allowed because this is our fudge factor. Now, this model might actually do much better on the second group. So now we're able to drop the second largest group error from 0.5 to 0.25, just because we gave a little bit of extra room for the first group. Now, this is still consistent with an idea of approximate Lexi fairness that we introduced before, because y2 prime 0.25 is still less than or equal to 0.5 plus alpha. But once we've committed to a model setting group 1 error rates and group 2 error rates within this range, we may be forced to set the third error rate to something that is higher than pointwise plus alpha approximation. So after we've locked in the first largest group error plus or minus alpha, locked in the second largest group error plus alpha, then the third group error is 0.25, which is much larger than alpha. And we give a more detailed treatment of this in our paper. So this was a very interesting discovery, and in order to come up with algorithms that we could generalize, that we could make substantial claims about, we had to find a stable definition of approximate lexicographic fairness. So the definition that we came up with is this. We defined approximate lexicographic fairness to be as follows. So we consider some L, some level between 1 and capital K, and some alpha greater than 0. And we let epsilon be a vector of approximations at each level that is always pointwise less than or equal to alpha. So we define this approximation recursively. We let the model H sub 0 epsilon be the entire model class H. So this is just a starting point. And then recursively, we say that H sub j of epsilon is defined as the models in the previous level that have the smallest jth group error rate up to an epsilon approximation. So we start with the whole model class, we trim it down to those that achieve a min-max error rate plus some epsilon, and then of those, we do the same thing. We trim them down to ones that achieve smallest second group error rate with some fudge factor. And one nice thing about this is that it includes the exact definition. So if you let epsilon be 0, then it can still be an alpha approximation. It's just that we set each epsilon I to 0. So a model H satisfies L alpha lexicographic fairness or Lexi fairness if the model is in capital H sub L superscript epsilon for some epsilon that is component-wise less than alpha. And again, this lets us apply generalization statements and make claims about our algorithms. So one remaining issue with this is convexity. So we would like a definition that is convex. for our algorithms, and a constraint on the highest error amongst all groups, which is the case for minimax error, is correct. But if we constrain the second highest group, the third highest group, etc., these constraints end up being non-convex when taken in isolation. So to get around this, we realize that we can replace constraints on the kth highest error group with constraints on the sums of all k tuples of errors. So if we know what the first group minimax error rate is, and we know approximately what the second one is, and we know what the first plus second one is. And we can do this first plus second plus third, etc. And this lets us narrow down our model space in the recursive manner shown in the previous slide. But the constraints that determine which models are in the space are convex. So for the rest of the talk, I will discuss the algorithms and claims in our paper. So we have already defined a stable and convex version of approximate Lexi fairness. We then go on to derive oracle-efficient algorithms for finding approximately Lexi-fair solutions. We show that when the underlying empirical risk minimization problem, absent fairness constraints, is convex, then our algorithms are provably efficient. And we show that approximate Lexi fairness generalizes. So an approximate Lexi fairness on the training sample implies approximate Lexi fairness on the true distribution with high probability. So now I will give an overview of the algorithms that we present in this paper. And here's kind of the overall workflow. So we will be rewriting our feasibility problem as a minimax problem. We'll show that the minimax theorem of Freund and Shapiro applies. And we will solve using no-regret dynamics. So in the regression setting, we'll have a learner that plays online projected gradient descent. In the classification setting, the learner will play follow the perturbed leader. Both of these are no-regret algorithms, and I will be focusing on the regression setting in this talk. In general, our approach to find Lexi-fair models will be to recursively find minimax rates. And our algorithm will return a model achieving those minimax rates, and therefore the model will be approximately Lexi-fair. So at each level j, in an inductive fashion, we will already have the minimax rates for the previous rounds, eta 1 through eta j minus 1, and we will want to estimate eta j. So now we can write a constraint and dictate that every sum of j group errors be a most eta j. This gives us the ability to write a Lagrangian. So here we are minimizing eta j, and then we have a penalty, lambda, on any sums of error rates that exceed the threshold eta for that number. We frame, at each level, we frame the problem as a two-player zero-sum game between a learner and an auditor. So at each round T, there will be weighting over groups determined by the auditor. The learner will best respond by computing model HT to minimize the weighted prediction error. I will also use theta to talk about the parameter space for the model, so those will be interchangeable here. The auditor will update group weights using online projected gradient descent, and then the learner's final model will be a uniform distribution over all of the models produced. So at each level, so we will have a data set. We will have the number of groups, a fairness parameters, L and alpha, and a loss function that determines our statistical model class. For the levels, J equals 1 through L, we will determine our number of iterations, which will be a polynomial in 1 over alpha squared. And then we will find a Lexi-fair model at that stage. We'll find the parameters theta for the regression model and eta j, which will be the new threshold. And we will be calling this game a game between a learner and an auditor, where the learner is playing online projected gradient descent. And we'll spit out an L alpha convex Lexi-fair model for theta at level L. So the subroutine that's called, here's the two-player zero-sum game. So we have the number of rounds T. We have our previous estimates A to 1 through A to J minus 1. And basically the learner will play the model that it's come up with, so theta and A to J. And then the auditor will best respond by choosing lambda, the dual variable, to penalize the sum that exceeds the threshold. The learner will update its actions using projected gradient descent, and then it will spit out an average play over those T rounds. And this will give us a Lexi-Fair model at level J. Now, the auditor's best response, as I alluded to before, basically what the auditor is doing at each round is that it is finding the groups that exceed their threshold, so the sum of 1 through R that exceed their threshold by the most, and then setting that lambda to some maximum value, and then iterating. So this framework spits out an approximate Lexi-Fair model. It's approximate to level L and with approximation factor alpha. And our ability to prove out of sample bounds relies on our definitional choice that ensures this stability. So we can show that if our base class H satisfies a standard uniform convergence bound across every group, so for a distribution P and any delta greater than 0, we have some group error gap, beta of delta, such that the chance that we have an out-of-sample error for that group greater than beta of delta is less than delta. And then we have a model that is approximately convex Lexi-Fair on our data set. And if the model is approximately Lexi-Fair on our data set, then it is approximately convex Lexi-Fair on the underlying distribution. So more technically, we say that for every data set S sampled IID from P, if a model H satisfies L alpha convex lexicographic fairness with respect to X, then with probability at least 1 minus delta, it is also L alpha prime convex lexicographic fair with respect to P for alpha equals alpha plus 2L beta of delta. So you'll notice that the approximation factor widens a bit. So we have alpha prime instead of alpha. And the difference between those two is an additive factor that's a multiple of the number of levels we've had to go down. And then our probability variable delta. And we can extend this to the classification case. So as a corollary, we have our statement here. And the important thing is that when we have 0-1 loss, the sample complexity is polynomial in the relevant parameters L, alpha, and the VC dimension. So if we have a class H of binary classifiers with VC dimension DH, then for every P and every data set S, consisting of groups GK of size N sampled IID from P, if a random model P satisfies L alpha convex lexicographic fairness with respect to S, then with probability at least 1 minus delta, it also satisfies L2 alpha convex lexicographic fairness with respect to P, provided that the minimum group size is determined by, again, a polynomial in alpha, L, and DH. And with that, I would like to thank you for your attention.